Let's get started with section 1. In this section, we will focus on understanding the architecture of IT systems. We will look at the common systems you typically see in the IT world and how they fit together. Because this will build the foundation for section 2, where we will move into OT and industrial control system architectures. So once you have seen the IT side, it will be much easier for you to draw parallels and understand how industrial systems are structured. And when you deeply understand how these OT and industrial control systems work, only then can you really think about their security. Only then you will understand where to put enforcement boundaries and what security controls make sense. Let's get started then. Now, before we start looking at different systems in the IT world, let's first understand what we mean by a system. So, by definition, a system is simply a set of components that work together to achieve a purpose. In other words, a set of things you have put together in order to do something. And in the IT world, if I have to give you a simplest example of a system, then take for instance your laptop. Your laptop isn't just one thing. It seems like one thing, but it isn't just one thing. It's made up of many components. On the hardware side, you have the physical body of the laptop, you have memory chips, storage, a processor, and on the software side, you have an operating system, browser, applications. So when all these pieces come together, when all this hardware and software come together, they create a system that allows you to do some kind of useful work. And the same idea applies to the OT ICS world as well. There, you see systems built from pumps, valves, sensors, actuators, PLCs, HMIs, all working together to control or run a physical process. And if you recall my earlier example of the water tank at home, that was the simplest example of the OT system. There, I had put some sensor, motor, and some pipes together to form a small OT system that automatically filled the tank with water in my home. And that was the simplest example of the OT system I was showing you. Now, in real world, in industries, the OT systems are far more bigger, containing hundreds or thousands of components and spread geographically around thousands of miles. And they are far more complex and far more bigger than the IT systems. And the OT terminology, the operational technology terminology, is an umbrella term. It contains both systems, IT systems and the industrial control systems that come together, integrate together, and work together to run a physical process. And that's the important point to notice, that systems don't work in isolation. They usually rely on other systems, either by sharing data or by sharing services. And this means that while each system has its own vulnerabilities, once they are connected, they produce new types of vulnerabilities, a new class of vulnerabilities because of these interdependencies. For example, with the ongoing digital transformation revolution and the Industry 4.0 AI revolution, several OT systems are becoming more and more tightly integrated with IT systems. And this IT-OT convergence, it brings huge benefits like efficiency and visibility, but it also creates critical dependencies. So if IT goes down, if IT system goes down, your OT ICS system can also be impacted. And that's exactly what happened in the Colonial Pipeline ransomware attack incident that I was discussing with you previously. In there, a breach in the a breach in the IT system environment, in the IT system, forced the company to shut down its OT system for safety reasons, which led to fuel shortages across several US states. So, the key takeaway from this slide is then that a system involves multiple components, which, when connected together, produce some desired results. And these systems, they don't work in isolation. They also depend on other systems. And OT system now is depending more and more on the IT system because of the digitalization revolution. And when one system depends on another system, it increases the attack surface of that system and produces new risks that we must address. So, with this basic understanding in mind, now let's move on and look at different systems that we see in the IT world. Now that we have understood what a system is, let's talk about system architectures. So, an architecture, in simple terms, describes the designed structure of something. Think of it like a blueprint. It explains how the different parts are arranged and how they work together. So, when we say system architecture, we mean a description of how specific components are deliberately put together to perform certain actions. For example, in IT, the architecture of a web application might show the database at one end, the application server in the middle, and the web front end that users interact with. Similarly, in OT, the architecture of a control system might show sensors feeding data into a PLC, which then sends commands to actuators to control some physical processes. Now, depending on the audience, we can represent architectures in different ways. And there are frameworks like TOGAF and Zachman framework that provide levels of abstraction, which means we can show a high level business friendly view for executives or a very detailed technical view for engineers. Now, why understanding system architecture is important? Because only when we clearly understand and draw the architecture of an OT or ICS system that we are trying to protect, we can decide where to put enforcement boundaries. For example, where should the firewalls go? Where do we need network segmentation? Which endpoints require stronger protection? And the architecture also helps us identify which components are most vulnerable. In a web application, for instance, the database and application server usually sit inside the internal network, but the web front end is exposed to the internet. That makes it the most vulnerable part, and so we know that it needs stronger protection. The same principle applies in OT, in ICS. So if you think about a data historian, which is like a database for OT world, that sits between the IT and the OT, collecting data from industrial processes and making it available to business systems like ERP or some SAP systems on the IT side. And we know that because a data historian has some components that are going to communicate both with IT and OT, it becomes a high risk component. So, by studying the architecture of the OT and ICS system, we will find out more components like data historian that we know are going to be dual home, that are going to talk to both IT and OT, and that can become pivotal points for attackers to move from IT towards OT. And that's why then we know that these are the components that we need to secure more. So that's why understanding system architecture becomes more important in deciding the right security controls and right enforcement boundaries for the most exposed parts of the system. That's all on this slide. See you in the next one. Now, let's start with the simplest type of system architecture, that is the client based system. This is actually the oldest form of computing. It was very typical in the early days of personal computers. In this model, everything happened on a single device. Applications were fully contained on that one system, the processing was done locally, and the data was stored locally as well. There was no dependency on a server or the internet. So think of an early standalone desktop computer where everything was run locally, all the applications were running locally, processing locally, and data was also stored locally. There was no need to talk to cloud, and there was everything was running locally. Now this was the simplest model, simplest system architecture, and but it came with limitations and vulnerabilities. First, authentication in these systems was often very weak or non existent. Many of these systems didn't have strong login mechanisms built in. Second, the data was stored locally in plain text, and the operating system did not have capability to encrypt it, and anyone gaining access to the device could read the data. And third, there's a big physical device risk. If the laptop, smartphone, or external drive is lost or stolen, all of the data stored on it could be exposed. So while these client based systems are simple and self contained, they highlight an important lesson. When security depends entirely on the physical device, losing control of that device means losing control of all the data. So, this architecture is the foundation. It helps us understand how computing started. And from here, we will see how things evolved into more complex client server and distributed models. So, now that we have talked about the client based systems, let's move on to the next big evolution, that is server based systems, which are also called as client server or multi tier systems. So, unlike client only systems, here we need a network connection because clients and servers must talk to each other. This is the model we commonly see in web applications. For example, when you open your web browser and visit a website, you are actually engaging in a client server interaction. So typically, server-based systems follow a multi-tier architecture. At the front, you will be having the client like a browser. Then you have a web server such as Apache, which handles the web requests. And behind that, there's usually an application server like PHP or Java that contains the business logic. And finally, at the back, you have the database server like PostgreSQL, where all the data is stored. Now, some environments may simplify this just into two tiers where the client talks directly to a server, but in modern cases, especially web applications, you will see multiple tiers working together. Now, from security point of view, every tier should authenticate its connections and enforce strict boundaries because if attackers can bypass authentication at one tier, they may pivot deeper into the system. And if we look at vulnerabilities, then vulnerabilities here are broader than in client systems because server-based network architectures, or sorry, server-based system architectures, they will often suffer from vulnerabilities such as unrestricted network traffic, weak authentication, unpatched software, lack of encryption, inadequate backups, and insufficient logging. So while the client server model enables far more powerful applications than standalone clients, it also greatly expands the attack surface. That's why each tier individually, securing each tier individually and securing the communication between the tiers becomes very important. It becomes absolutely critical. Otherwise, you will have you can easily have the whole system compromised. And the bigger the system, the more costly it is, the more complex it is, and the bigger tasks it is handling. So yeah, that's all on this slide. Then see you in the next one. Now, in this section, let's talk about the last system architecture, that is about the database systems. Database systems are the most critical components in any architecture because when we talk about databases, one thing you must remember is that they carry a very high hack value. Why? Because databases hold massive amounts of information. If an attacker gains access to a database, the payoff can be huge because databases can hold customer records, payment details, intellectual property, or in the OT world, they can hold production process data, and this data can be sold, leaked, or used to disrupt operations. So, database systems are among the most critical parts of any architecture. And a database system, how it works, it uses DBMS or database management system that is used for managing and organizing data efficiently. And you run some CRUD operations, CRUD meaning create, read, update, and delete. These kind of basic operations you run to interact with the data. And important thing to notice is that databases allow multiple users to access and share information at the same time. And that then brings in a lot of vulnerabilities. Some of them are straightforward, like a weak access control or lack of encryption can produce a huge risk for the database. But there are also these aggregation risk and inference risks that come with the database systems. Aggregation risk meaning that even if individual pieces of data look harmless, when you combine them, you can learn something sensitive about them. And now with AI, this is becoming more common. This risk has increased because with AI, you can combine individual pieces of data and then learn something sensitive about the data. For example, A hospital database might separately list patient IDs and treatment codes, use segmentation to store these data into different tables separately. Neither of them looks too revealing on their own, but if an attacker combines them using some kind of AI, then they might figure out which patients are receiving treatment for a specific disease. And then this brings you in direct violation with regulations such as HIPAA and other healthcare regulations and PII data regulations. Then you also have inference risk, which is when you can guess restricted data indirectly. For example, let's say salary details of employees are restricted in an organization, but if a user can see departmental averages, also knows the salaries of a few individuals in that department, then they can work backwards to infer the salary of the person whose data is supposed to be hidden. So like this, now with AI, these risks have increased because these permutations and combinations can be run fast, and one does not need to be very intelligent in order to play with these combinations. So yeah, for database systems now, the aggregation risk and inference risk has increased a lot. And in IT, databases at the heart of the things like online banking, shopping carts, and social media feeds. Whereas in OT, databases often take the form of historian databases that store sensor readings, alarms, and that process some real-time logs. And if attacker can corrupt that data historian, then operators could lose visibility or they may be tricked into making some wrong decisions. So it's important to understand that databases are high value assets, and whenever you are thinking of enforcing boundaries in your systems to protect some components, database system is one of the most important component that should have some kind of high security controls around it. All right, then that's all in this section. See you on the next slide. All right, that brings us to the end of section 1. Let's quickly recap what we have covered in this section. So we started this section by introducing the concept of a system and an architecture. We looked at what we mean when we say system, which is simply a set of components working together to achieve a purpose. We also discussed that systems rarely exist in isolation. They depend on each other, share data, and share services. And that interaction improves efficiency and visibility, but at the same time, it also increases the risks and expands the attack surface. Then we explored some common system architectures in IT systems, such as client-based systems, the simplest kind, which run locally on a single device and have risks like weak authentication and data exposure. Next system that we looked in IT system was server-based systems, which are more complex, multi-tier designs, and that you usually see in web applications. And then finally, we studied the architecture of the database system. Now, database systems, they hold massive amounts of valuable data, which is the reason databases have very high hack value for attackers, and which is why protecting them with strong controls is so critical. So by understanding these three main architectures, client-based, server-based, and database systems, we have built a foundation for how systems work, how they interact, and where their vulnerabilities lie. Now, this foundation is going to help us to move into section 2, where we will shift our focus from IT systems, from IT world to the world of industrial control systems and operational technology systems. And there we will break down the critical component of the ICS world, how the architecture looks like, what makes them unique from IT. So with that, let's move forward into section 2 and let's explore the world of ICS and OT.